We're going to be looking at section 8.2, part 1. We're going to be looking at vector valued functions, or just the vector functions. So in this lesson, we're going to be assumed that you understand the basics of vectors. Watch the video of vectors from pre-calc if you need to refresh your understanding. Just let me know. I'll give you access to it. So what is a vector value function? It is a function or a vector function. Okay, R, and this symbol right here, remember there's a vector symbol. It's a function of t whose domain is a subset of the set of all real numbers and whose range is a set of vectors. The notation that we need to be familiar with that could be appearing is component form, the most common one. If you remember, it's going to have these little pointy brackets like so, and here this vector is broken up into a horizontal and a vertical. Unit vector, ij, also known as linear combination form. It's just these quantities right here with a vector I, meaning that's in the horizontal direction, and this one times j, which is in the vertical direction. And then also, vector forms and stuff is basically just parametric equations, so you can actually have the vector in a parametric form. And they are pretty much means the same thing. If you look at it closely, it's the same thing. Okay? So here's our first example we need to focus on when we deal with the vector stuff is what is our domain. So let's go ahead and take a look at this right here and see if we can figure out how to find the domain of one of our functions. Let me move this over here. So find the domain of this vector valued function right here. And so obviously it's pretty obvious what you're going to do. You need to find the domain of each piece. Okay? So what is the domain for the natural log of t minus 1? Well, natural log, obviously this argument right here can never be 0 or negative. So the number that makes this 0 is 1. And so we know that the domain is all the t values that are greater than 1. And for this function, what's the domain? Well, it's in a fraction form, and there's a square root. The square root means that the t can never be negative, and because it's in the bottom of a fraction, it can also never be 0. And so we know that t has to be greater than 0. So if you just basically do a number line overlap of each of these things, you can kind of see how it lays out. I have here's 0, here's 1. The bottom one, not counting 0, but it has to be greater than that. And the top one has to be greater than that. And so the overlap is your domain, which means this part from 1 on is my domain of this function. So based off of that, my domain of this vector value function is the t greater than 1, or you can write it in interval notation like so. Okay? The next part we want to talk about is limits. Okay? What are the limits of a vectored value function? See if I can get the focus a little bit better than that. So if I have a vector valued function defined as this, and some real number a, then the limit as t approaches a of that vectored value function would be the limit of each of the individual parts of it in the component form. So we have to do both of those, and it's provided that those limits both exist. So both of these limits have to exist for this limit here to exist. So that is our definition. And so let's go do one to see it worked out. Find the limit of this vector value thing. And so I need to find the limit of each of those pieces. Okay. So what is the limit as t approaches 0 of e to the negative t? And if I plug in 0 in here, we get e to the 0, which is 1. And the limit as t approaches 0 of the sine of t over 2t. Okay. If I try to plug in 0, we can see that I'm going to get the indeterminate form. Okay. This is the indeterminate form, and so I can use L'Hopital's rule. So this will equal to the limit as t approaches 0, the derivative of the top, the derivative of the bottom, and then I can do the substitution for 0, and I get 1/2. This is one way of doing it. You could have done it a different way, but you could have factored out the 1/2, and then you would have sine of t over t, which we know equals 1 as t goes to 0, and we got 1/2 times 1. That would have been another approach to this. You didn't have to do L'Hopital's rule. Okay? So when I get done with this, I have to write my answer. So what is this limit over here? So my answer is the limit as t approaches 0 of this vector valued function is equal to the vector 1, 1/2. Or you could have written it in combination form, just showing that how I would take this and write it into ij form. I would write vector I, 1 times vector I, plus 1/2 times vector j. So I can write it this way or this way, but it has to be written in vector form. Okay? So the next question we have to look at, or the next item, is continuity. A vector valued function, defined as such, is continuous at a real number a if, and you'll notice that it's pretty much the exact same definition that we had previously for just a regular function. The vector at a is defined. The limit as t approaches a of the vector exists. And the limit as t approaches a of the vector has to equal the value, the vector at a. And so you'll notice the similarity of continuity of a function at a point is very similar to what we need to be doing. Okay? And so let's take a look at this right here. I have some functions over here we want to look at. Determine which of the following vector value functions are continuous for all values of t. So look at how it's written. The way they write it is continuous for all values of t. That means every value between negative infinity and positive infinity. Because, as you're going to notice here, let's take a look at this one. If I have this right here and t squared and the tangent of t, t squared is continuous for all values of t, it's fine, but the tangent has vertical asymptotes. So it will be continuous on its own domain, but it is not continuous for all values of t. And so that's what we have written right here. It's not continuous at plus or minus pi over 2, plus or minus 3 pi over 2, and so on, which is where the vertical asymptotes are, because, so that's why it's not going to satisfy that one. Over here, this is a polynomial, so it would be continuous everywhere. This is e of t, so it's continuous everywhere. So that one is continuous for all t. Here I have a square root, so clearly I can't plug in values less than 0. Cosine is continuous everywhere, but I have a restriction here on this one. We can't have t less than 0, so it is not continuous for all values of t, but it is continuous for which this vector is defined. Since the domain of this function is t has to be greater than or equal to 0, this vector would be continuous on that, but not for all t, because it can't be less than 0. Same concept over here. Sine is continuous everywhere, but this one has a point that is not, because you're going to have a vertical asymptote at positive 2 for this piece. But on its domain, it would be continuous, but not continuous for all values, because when t is 2, we have a problem. And this vector over here, this is a constant vector. And since there's no t's on it, then clearly it's going to be continuous for all t's. Okay? So that's kind of how that works. Down here, we're going to be looking now at derivatives. How do I take the derivative of a vectored value function? And you probably guessed it, I'm literally just going to take the derivative of each component part. Okay? There's your dx dt, your dy dt, because remember, it's very similar to parametric, and that's how we do parametric. Okay? So let's go take a look at some examples after we do some properties. Here are some properties of rules that we want to follow, which are pretty much identical to what we had before. So I have vectors, so how do I do scalar multiplication? So if I have a scalar number times a vector, then the derivative would just be the scalar times the derivative of the vector. The sum difference, just sum difference. Multiplication by a function, so this is some function of t times a vector of t, and so you'll notice that you got to kind of do the product rule here. And remember, since these are both vectors right here, you're still going to have a vector answer on this one. And this is the product of two vectors themselves, and again, product rule format. Okay, so with that, we're going to do some examples. Let's find the derivative of this vector right here. So we want to find the derivative of each piece that's in here to find the derivative of that. So what is x prime of t? This is x of t, so the derivative of the sine is the cosine. So I'm going to have the cosine of 2t, and then chain rule says I have to multiply this by 2 also, giving me 2 cosine of 2t. Y prime, the derivative of the cosine is minus the sine. So I'm going to have negative sine of t over 3, and then chain rule says I have to take the derivative of that, which is going to give me a 1/3. And bringing everything together gives me a negative 1/3 the sine of t over 3. So with the derivative of each of those pieces, I can find the derivative of the vector r, which is going to be a vector itself with these items in it. And there you go. Okay? Which I want to reveal this little bit down here just so you can have it. The difference between a vector and parametric is that the vector value function derivatives are written as vectors, and the parametric derivatives are written in this fraction form right here. Okay? This is dy dt, this is dx dt in vector form. Here's what it would look like in parametric form. Okay? All right, so let's look at another example that I have. Find the tangent vector to the curve, cosine t, sine t, defined for t between 0 and 2 pi at t equals pi over 4. Okay, so as soon as we start talking about a vector, we're going to need the derivative at a point. Okay, and so we got to find that out. So let's find r prime, and so vector r prime of t, we already know is x prime of t, y prime of t. And so the derivative of each of these things is going to be, the derivative of cosine is minus the sine. The derivative of the sine is the cosine. So there's that. We want to take this and we want to find its value at pi over 4. So this is going to give me a negative sine of pi over 4, cosine pi over 4, and you're going to get this vector right there. Okay, so what does this basically mean? Okay, so let's go take a look at it. I'm going to show you the answer page that I have over here instead of redrawing it. So what I have going on over here is I have this vector is on a cosine sine, which is a circular fashion, and here's angle pi over 4 for t. Okay, and this vector means from standard position I go over square root of 2 over 2, negative direction, and then up to here. So it's that, but since it's a vector, this is just the standard vector of any vector in the plane, so I can find an equivalent one right off of that point over here off this angle. And so what you have here, this curve is going, if you start plugging values in, you're going to get this circle going in this direction. And so from this point right here, you're going to have the velocity of this vector from this point outward. And that's kind of, if you think about it, if this thing is spinning that way, when I release something on a string, it's going to fly off in that direction. That gives me that velocity in that direction. So that's kind of how this is used. Okay, so take a pause here, write this little part down. Hopefully I can get it to focus. Things don't want to focus for me today. Okay, so it represents the velocity of a point moving around this curve at pi over 4. That's basically what it boils down to. Okay, so let's take a look at the next problem. So given the vectored value function, r of t is this, find the derivative and the second derivative. Okay, so let's find r prime of t. It's going to be the vector. We take the derivative of this quantity right here, which is going to be 5 e t squared plus t times the derivative of that, 2t plus 1. And then the derivative of this over here is u prime over u, so that's the u. And then the derivative of that is 2t plus 1. That is r prime. Okay, so how do I take the second derivative of that? Well, let's take the derivative of these things. We're going to have some product rule going on in here, but that's pretty much what we have to end up doing. Okay, so it's going to be a little bit long. Here's my first. This is my second. So it's the first times the derivative of the second plus the second times the derivative of the first, which is just basically this whole thing again. And that's the first part. Now I have to take the derivative of that, so you can see clearly we have the quotient rule, so which is going to be the bottom times the derivative of the top, and then the top times the derivative of the bottom, all over the bottom squared. So that is the second derivative. So depending on your situation and what you need to do I need to simplify this, clean this up, what do I need to do? You can, or you can just leave it. It just depends on what they're going to ask you next. If you wanted to try and simplify this out, this is one possible way to do it. There's this quantities in both of these, so I can factor the whole thing out of that. And then I'm going to have something multiplied left, so I'm going to have a 2 from there. And I'm going to have this times that, so that gives me that thing squared. Over here, you can multiply everything out on top, combine like terms, and you'll end up with something that looks like this. So if you needed to clean it up and look at it differently, there it is. Okay? Let's look at the next item we want to figure out how to do, and that would be integration. So we have indefinite integration and definite integration, and you probably guessed it. It's basically the same thing. You're just going to take the integration of each individual piece that's on the inside. As you can see here, don't forget to put in your plus C's. Notice in here, if you look closer here, that I have subscripts on these C's because they are not the same. And you need to make sure you do the same. They're not the same C. They're two different functions, two different C's. You need to distinguish between them by doing subscripts. Okay? Other than that, this right here, you just do your fundamental theorem of calculus. Just take the integration and evaluate it at the limits. That's what we have going on over here. So pretty straightforward. Let's go ahead and look at an example. You'll see that it works out pretty easily. So here's our function, our vector v, right here. Let's find the integration of v. Okay, so I know the integration of vector v with respect to t is going to be the integration of each of these pieces, t squared dt, and the integration of 1 over t dt. And there you go. So this is going to be t cubed over 3 plus some constant. And this over here will be the natural log of t plus some other constant. And there you go. We are done. Okay. Let's take a look at a definite one where we have limits. So once again, from 0 to 1 of vector v is the integration from 0 to 1 of each of these. And you should make sure you write down what things are. Don't try and, skimp. You're showing them that you know what you know, that you know how to do it. Once I have it written out, then I can integrate each piece using U substitution if necessary along the way. So I would do U substitution here. And double check my work. But you should get negative 1/2 e to the negative 2t. And then over here you're going to get the natural log of t plus 3. And we're going to evaluate this vector from 0 to 1. Okay? So then we're going to plug in 1 minus upper minus the lower. So this is going to be a negative 1/2 e to the negative 2 times 1 minus a negative 1/2, which makes this plus 1/2 e to the 0. Over here, if I plug in 1, I'm going to get the natural log of 4 minus the natural log of 3. Because these are numbers, I don't need the absolute values anymore. They're already positive, so I don't need them to guarantee positiveness. So working everything out, simplifying some things out, you're going to end up with, the first one here, I have a negative 1 over 2e squared plus 1/2. And then over here, like I said, the natural log of 4 minus the natural log of 3. But I can go even farther with this. Okay? I can go even farther with this. This right here, I can get a common denominator, okay, and bring it together as one fraction. And if I do, it can look like this. E squared minus 1 over 2e squared. And this, I can use condensing rules because of a minus sign and write this into a single natural log of 4 over 3. So that's some ways I can simplify my answers. Okay? So be aware of those so that you can, if it was a multiple choice question, you can find the correct answer down below. Okay? Let's do this one right here. This time you notice it's in IJ form. Find this right here if r, vector r at 0 is that. Okay? So since r is the integration of this vector right here, let's integrate this vector right here. So what is r of t? Okay, it's the integration of this piece plus the integration of that piece. This piece over here is the sign. You're gonna have to do the U substitution process here to get your full complete answer. You're gonna get a negative 1/2 the cosine of 2t plus some constant 1 times vector I. And then over here you're going to get the arc tangent of t plus another constant, vector j. So that is what that is. So how do I find this? Well, I got to find out what these c's are. All right. So what is it? I know then t is 0. I have this. R turns into that. So at t equals 0, what is r prime of 0 going? I don't know why I put a prime in there. Oh, I'm looking at the wrong question. Sorry, my bad. I was looking at the problem below. So what is r at 0? Plug in the 0 in here. We're going to get negative 1/2 the cosine of 0 plus some constant 1. And then over here we're going to get the arc tangent of 0 plus constant 2, and that's j. And cleaning all this up, I'm going to get, this is a 1, I'm going to get negative 1/2 plus c1. And then the arc tangent at 0 is 0. And so I'm just going to get c2 here for j. Now, let's do some comparison. So if at 0 this thing is supposed to be 1/2, then I know that a negative 1/2 plus c1 has to be 1/2. And solving this out gives me c1 has to be 1. Likewise, the constant out in front here is 1. That tells me that c2 has to equal 1. So my final answer then is going to be negative 1/2 the cosine of t plus 1. And then this will be the arc tangent of t plus 1 vector j. And you can also have written it in component form, but because it gave you ij form, you should write your answer in ij form. Okay? The last example that I have here, we want to find r, and I gave you the second derivative and some initial conditions. So you're just basically doing integration techniques, getting this back up to r from r double prime. So we want to find r prime of t, which is the integration of vector double prime of t dt, which is the integration of each of these pieces. And then minus the integration of 6j. And so if you work this out, you're going to get a negative 4 sine of t plus 1 constant, and then minus 6t plus another constant for the j. And just like we did up above, we have initial conditions here. So at t equals 0, r prime at 0 is going to be a negative 4 sine of 0 plus c1 vector I, and then 6 times 0 plus c2 vector j, and that's supposed to equal 3j. Well, that tells me what? Well, sine of 0 is 0. There is no I part, so this whole thing has to be 0, which tells me then that c1 has to be 0. Over here, this negative sign times that gives me negative c2 has to equal 3, which leads me to believe then that C2 must be equal to negative 3. And once I know that, then I can integrate this out. Okay, R prime of t is a negative 4 sine of t, and then minus 6t minus 3j. So that's what R is right there. And we want to find R prime, excuse me. And so R is just the integration of that. And we just do it one more time with this vector right here. So we're going to integrate each piece, and negative 4 sine of t dt, and that will be for I, integration of 6t minus 3, and that will be for j, and then you can get your answers from there. 4 cosine of t plus another constant, I call it C3, and then this over here is 3t squared. And again, I'm going fairly quickly to make the video a little bit shorter. You should double check all my work just to make sure I didn't make any mistakes. And so we have to find these values, these C1, C3, and C4, again using this one right there. So at t equals 0, R of 0 is going to be 4 times the cosine of 0 plus C3. And then in here we'll have 3, 0 squared minus 3 times 0 plus C4, like so, which gives me 4 plus C3 I minus C4 j, and that has to be 2I. What does that tell me? That C3 is is negative 2, and that C4 is equal to 0. And so I can write my final answer here for vector t as 4 times the cosine of t minus 2, vector I, 3t squared minus 3t, vector j. Okay? So that's kind of some things you might be asked to do using vector stuff, derivatives, integrations, and keep in mind that it's very similar to parametric. So you might have a question that's in this form that we saw in the parametric in the last video, but it could be in vector form. You just go through the same process that you would have done for that one. Okay? And we'll do more examples and practicing as we move along. So that ends this video. Here's what this page looked like. I'll pause it. Down below, here's that example we just did. If you want to see all the little small stuff, but there's nothing really extra that I didn't really do. Okay.